Welcome to part 2 in our discussion of simple linear regression. For this part, we're going to talk about how we actually obtain those particular values of the intercept and slope for simple linear regression. Simple linear regression, it's a very powerful tool for fitting a line to a scatter plot of data, as we've talked about. And this line is defined by this equation in which we have our fitted or predicted values of our outcome equal to an intercept plus a slope times the raw values of our input or predictor variable, or x variable. And we can further partition our outcome into what we call the fitted and residual or error components. So the fitted part or predicted part, that is described by our line. And then the residual or error part is just whatever's left over. So we can say that we have that part of the outcome which is described by our line, and that part of the outcome which is residual, it's left over. This is cool, but we might not say, where do we actually get these particular values of the intercept and slope? So for the example of cricket chirps per minute, we get this particular value of the intercept. So when x is 0, when the number of cricket chirps per minute is 0, we get this expected mean temperature of 37 degrees Fahrenheit. And then we have this value of the slope for B1. So for every 1 unit increase in cricket chirps per minute, the temperature is expected to increase by 0.23 degrees Fahrenheit. But where do we get these particular values of the slope and the intercept? Where do they come from? Because keep in mind, a line is described by two numbers, an intercept and a slope. So when we change the values of the intercept and slope, we have many different lines. And in fact, there are lots of different lines we could fit to the scatter plot of data. Now some might look a little off, but we could still fit them to this scatter plot. How do we pick one particular line out of all these almost infinite range of possible lines we could fit? Well, we use a method called the method of least squares. That's why sometimes you will hear simple linear regression called least squares regression. Right? It's because we use this particular criterion, we use this particular algorithm, this method for fitting this line to a scatter plot, for finding particular values of the intercept and slope. And so sometimes you'll even hear least squares regression called ordinary least squares. It's so commonly used. Well, what is this criterion? The idea is that we try to find those particular values of the intercept and slope. Right? There's one value for the intercept and slope such that when you add up all these squared errors, that sum of the squared errors is as small as possible. It's the least squares method. Right? We're trying to get this sum of squared errors and make that as small. It's the least squares. Well, what are the sum of the squared errors? Well, it's exactly what it sounds like. This is one nice thing about statistics. The language is pretty transparent. So when somebody asks you, what is the sum of the squared errors? You can say, well, you add up all the squared errors. It's the sum of the squared errors. Sometimes the sum of the squared errors, it's called the sum of the squared residuals. And that's because the errors or residuals, it's synonymous. It means the same thing. The idea behind this criterion, the idea of minimizing the sum of the squared errors, it's that we want the estimated or expected values on our line, we want them to be as close as possible to the raw actual values of our outcome overall. So if you recall, the residual error, it's the difference between the observed or raw outcome value and the value on our line, our fitted value. So the residual error for each observation, for each row of our data set, it's our raw value minus that fitted or residual, the fitted or predicted value. So it's y minus y hat. That is the residual error for each observation. And that y hat, it's based on the intercept plus the slope times the raw value of x. That's where we get the y hat. That's where we get the fitted or predicted value of our outcome. So intuitively, you can think of the sum of the squared errors. It's simply the deviations or distances for each observation squared so that they're positive, because we want to make sure that they don't cancel each other out. And then we just add them all up. We take these deviations for each observation and we square them. And we typically want a relatively small sum of squared errors. Right? We don't want our line to be that far off from our raw values. Well, how do we calculate the sum of the squared errors? Well, this is using the sigma notation that we described earlier. Right? We simply take each residual, we square it, and we add them all up for each row, for each observation. That's it. And one way to write out the error or the residual is our raw value of the outcome minus the intercept minus the slope times a raw value of x. Or equivalently, it's y minus y hat squared for each row. So if we have a data set with 7 rows, you're going to have 7 squared residuals, squared errors that you add up, right? So let's think about what this is really doing. When we have a different line, we have all these different lines. Each line has a different sum of the squared errors. That's because the sum of the squared errors depends on our raw value of the outcome minus our y hats. And those y hats are based on a particular intercept and slope. Right? The raw x values don't change, but the intercept and slope values change. So that's really why we have these different sum of the squared errors. So this line is a sum of squared errors. This line is a sum of squared errors. And so we have these different values for these sum of the squared errors. And we want that line that minimizes the sum of the squared errors. How do we calculate the sum of the squared errors? Well, we'll go through an example. The idea is that we want our data to fit the line such that this sum of the squared errors is minimized. Right? So let's look at our cricket data. In the case of the cricket data, we've already examined the least squares regression line. So let's just see what the sum of the squared errors is for our cricket data. We have this regression line. Right? We already know that this is the least squares regression line. So our model is y hat equals 37 plus 0.23 times x. 0.23, that is our slope. 37, that is our y-intercept, or constant. So for each row of this data set, we can calculate a fitted or predicted value. This is the expected outcome. This is the expected mean temperature for different values of x. So when x is 81, when there are 81 cricket chirps per minute, the expected mean temperature is about 56 degrees Fahrenheit. That's that first row's expected value. That's our fitted value. That's our y hat. For the second row in our data set, when x is 97, when the number of cricket chirps per minute is 97, the expected temperature is 60 degrees Fahrenheit. When x is 103, when there are 103 cricket chirps per minute, the expected mean temperature is 61.4 degrees Fahrenheit. When x is 123, we have 66 degrees Fahrenheit. When we have 150 cricket chirps per minute, the temperature is 72.27 in terms of its expected value. And then when x is 182, the expected mean temperature is about 79.6. And when x equals 195, the expected mean temperature is 82.6, roughly, degrees Fahrenheit. So we have these 7 different y hats, these 7 different expected means of the outcome for these different values of x. Now, accordingly, each observation has its own error term, its own residual. That's simply reflecting the fact that the y's and the y hats differ, right? Now, the y and the y hat can be the same, but typically the y's and the y hats are different. So in this case, for the first row, we have a residual of negative 1.86. That's because the raw value is below the y hat. The y hat is 56.36 degrees Fahrenheit. The raw value is about 54.5. So that's why we get that negative value. In the second row, we have that the raw value of the outcome is 59.5 degrees Fahrenheit. The expected value of our outcome is 60.05 degrees Fahrenheit. So we get this negative residual. So we can see we have positive residuals. We also have some negative residuals. Okay, the key point here is that the negative residuals, right, indicate that the raw values are below the line, while the positive residuals indicate the y's are lying above the line. And so we have some error. We have some residual part of the outcome, because our line, it's describing a lot of the variation of the outcome, but not all the variation. Right? Some of the y's are above, some of the y's are below this line, these actual fitted or predicted values of y. All right. The key point here, though, is that each row, each observational unit has its own residual, its own error, and then accordingly, each observation has its own squared error. right? We just take the residual, the error, and we square it. The reason we do this is that we want to add up all these errors, but if we didn't square them, then they would cancel each other out. So we want to make these errors positive. A very simple way to make these errors positive so we can add them all up and get an idea of the overall amount of difference between our y's and our y hats. One way to really do that is to square them. You could also take the absolute value. That's a different approach, but for really purposes of calculation, it's easier to work with squaring these residuals. So what we're going to do is we're going to square each error or residual of this data set. So for that first row, the squared residual is 3.47, or the squared error is 3.47. And you can see that we're turning some of these negative residuals into positive values, right? That's what the squaring does. We want to make sure that all of these errors, right, we're still capturing some of the error. We're just squaring them so that they are positive. So we have these 7 squared errors. All right? Then what we do is we want to add these all up, because that's all the sum of the squared errors is. We take all the errors, we square them, and then we add them all up. It's the sum of the squared errors. So for the sum of the squared errors, we just add them up. Right? So we already calculated these squared errors. So if we add them up, we get 3.47, 0.31, so on and so forth for each row of our data set, for each observational unit. And we get this value of 11.7. All we're doing is we're taking these errors, all right? It's the y minus the y hat. We square them so they're positive, and then we add them all up. We calculate the sum of the squared errors. And we get this value of 11.7. This is the sum of the squared errors for our cricket chirps line. We know that this is the least squares. This is the minimum sum of the squared errors, because this is based on a value of the intercept and the slope such that the sum of the squared errors is minimized. That's because we use the intercept and slope, those particular values, based on the regression line from this previous section of this lecture. So we know that this is the sum of the squared errors. Any other line we fit to the data set is going to have a larger sum of the squared errors, because we found the intercept and slope such that the sum of the squared errors is minimized. So any of these other lines, they have larger values of the sum of the squared errors. So you can see that when we fit the least squares regression line, or the classical linear regression line, it's those values of the intercept and slope, such that the sum of the squared errors, you take up all these errors, you square them so they're all positive, you add them up, that one quantity, that quantity is as small as possible. It's minimized for this particular data set. So since we derived the sum of the squared errors in this case based on the value of the intercept and slope from the least squares method, we know that this is 11.7. That's the minimum. Any other line you fit to the scatter plot, it's going to have a larger sum of the squared errors. Right? So that it really encapsulates the idea of the sum of squared errors, the least squares method. For each possible line we place on the scatter plot, we have a different intercept and slope. And these different values of the intercept and slope will give us a different y hat. And because the error is y minus y hat, we get a different error. We get a different sum of squared errors. Right? Now, in this case, by minimizing the sum of the squared errors, which is 11.7, we find that the intercept and slope associated with the sum of squared errors is the intercept of 37 and the slope of roughly 0.23. And with that, we have finished our discussion of the idea behind the sum of the squared errors, and we will continue in just a moment about really what it means, how we actually find the sum of squared errors that are minimum so that we can grab an intercept and slope for our regression model.